very extensive concept of a very robust grid throughout Europe. In other countries, they're going beyond planning. In some countries, they're actually constructing the lines today. This is China. China's doing a very, very aggressive plan to put very high voltage lines, much higher than we have in this country. Our highest AC lines are 765 kV. China's putting in 1,000 kVA lines in a number of places. Again, in many instances, to move location-constrained solar and wind resources from their western provinces areas to, again, load centers where they have their main population centers and manufacturing in the east. And they're actually doing it today. They're not talking about it. They're not planning. They're not worrying about cost allocation. They're just doing it. It's ultimately getting done. So let me talk about another area when I talk about reliability and stabilizing the grid and how we're going to do that. All of you here may see an automobile. What I see is a grid stabilization tool. Okay? What this is a Toyota Scion that was driven to FERC in November of 2007 from the University of Delaware. University of Delaware team took this Toyota Scion and they took the guts out of it. They took the internal combustion engine out and the transmission and they replaced it with an electric motor and with lithium-ion batteries, and they turned it into an all-electric vehicle, an 18 kilowatt-hour car. And in addition to doing that, it has about a 120-mile, 130-mile range. They drove it down from Delaware to FERC to Washington, D.C., and they parked out in front of our building. We plugged it into a 220-volt circuit, and they had and we ran it through a meter so we could see what was going on. And they had some other little devices in this car. They put into the car what they call an AGC, an automatic generator control, that is the same controller that is in a combustion turbine or a combined cycle gas plant that is used by the grid operator to signal that gas plant to run up and down so it can provide what they call regulation services. And regulation services, remember I told you that grids have to be stabilized in control areas, and you have to make sure the loads match the resources that come in. And so if you can't do that, you've got to somehow call upon those resources, those generators, to match it with what they call regulation services on sort of a 3-minute schedule, a 3-minute or less schedule. You've got to make sure that every little minute you got that load matching. Even though the load may be going up, it looks like a smooth curve, but if you look at it, sort of a micro view of it, you're in essence seeing it go up and down all the time because people are turning the lights on and off and turning their air conditioning on and off, etc. All that stuff is going on and off all the time. So you have to have the grid matching it, and the way they match it right now is with these fast cycling gas units. Well, you can do the same thing with a car. The car, in fact, can match that cycle. And in fact, we did that. And here is the car over a charging cycle actually matching the regulation cycle. The car is charging in this green line. The green line is going from 0 charge up to 100% charge, okay? Or a little above, actually, 98% charge. And it did this over a 6-hour period. Okay, this was actually night charging. It was doing this. At the same time that it was charging, it was receiving this blue regulation signal from PGM, from the grid operator. It was actually coming from the grid operator. And it was matching that blue signal with a red signal. And so each time a regulation signal would come in, it would match that regulation signal, it would go up and go down. And as you can see, in doing that, it was still charging. And it was not discharging the battery was actually charging at the same time. So what it was doing is matching the regulation signal and at the same time charging the battery in the car. What did that mean? Well, it meant a couple things. Number one, this car was stabilizing the grid. This car could have helped more wind get into the grid system. What it also meant was the payments that normally would have gone to a combustion turbine to provide regulation services, which happened to be the most expensive level of services for the grid except for energy and capacity, would be paid instead to this car. So right now there are 3 Toyota Scions that have been converted to all-electric vehicles that are at the University of Delaware that plug in at night and charge. And when they plug in, they get paid by PGM to provide regulation services. And they're getting paid somewhere in the neighborhood of $7 to $10 per day per vehicle. So we're talking about $3,600 a year to charge your car. So what does that mean? Well, Let's see what it means for an electric vehicle. I call it the cashback hybrid. If you take a standard internal combustion car and you purchase it, relatively, lower level car, $17,000 car, over its lifetime with gasoline maintenance, it's going to be the cost of the car. If you take, say, a Prius, which isn't a plug-in, but it does have a battery that helps you increase, in essence, the mileage of the car. Prius is going to cost you a little more, maybe $22,000, but ultimately it's going to, at some point in time, pay itself back over the incremental cost of a car that doesn't get better mileage than it does, just a straight internal combustion engine. Now, what if we take a plug-in hybrid electric vehicle, but that plug-in doesn't provide regulation services? It's going to cost quite a bit more than a Prius. But ultimately, it's going to get a payback as well, because it's getting its electricity solely from the grid. The Prius has to use gasoline. That electricity from the grid, to the extent you're driving it, within its range, it's going to cost you somewhere to about $1 equivalent of gasoline. So depending upon what you pay for gasoline, it's going to be a pretty good deal. But the problem is its batteries are going to be very expensive, because you need a lot of battery to get a 40-mile range, or even like the Scion I showed you to get a 120-mile range. That battery is going to be very expensive. But what if, in fact, you started getting regulation payments? What's going to happen? Well, this is what's going to happen. You're going to ultimately pay back the cost of that, incremental cost of that car, much, much quicker from a standpoint versus a internal combustion engine. You're going to do this, I calculated here, in less than 4 years from an incremental cost. So this type of interaction with the grid that is not a pipe dream, is not something 5 or 10 or 15 years in the future, but is happening today in PGM. PGM is paying now cars to do this today, can help us move to an electric transportation system that has all kinds of benefits, but one of the biggest benefits for this conference is the ability to integrate in renewables into the system, because it can help us significantly integrate renewables into our system. And so if we look at that type of integration, there are other things that will do this as well. And I'm going to talk a little bit about the smart grid that Roger talked about, and then I'm going to wrap this up. Distributed energy systems, certainly. Storage in the upper left of this slide here is a flywheel system that is used for storage. That's going to help us integrate wind into the system as well. And in fact, there are now 5 megawatts of flywheel storage on the New England ISO, Independent System Operator grid. There are going to be 20 megawatts very shortly on the New York ISO, Independent System Operator grid, again, helping to integrate wind to provide regulation services into the grid and also spinning reserve services. Another storage system down here in the lower left is Ice Systems Ice Bear. I just saw where Ice Bear, it's a company out of Colorado, just got a 50 megawatt contract with the Southern California municipal utilities to put in these systems. Ultimately what they do is they store ice at night. So when wind may be off-peak and generating more energy than we need, we can put it into systems like this to generate ice during the evening times, and during the day that can be used to cool the house. So ultimately, again, you're shifting your usage. And we have then some distributed generation gas systems, and of course down in the lower left we have the PV systems on your house. All these systems are going to help us integrate central renewable systems in further. But when we go beyond that, we talk about sentient buildings. I want to talk, Roger, about sentient toasters. That's what I want to talk about. I want to talk about toasters that are starting to take over here. We're going to have ultimately smart consumer controls. You're going to be able to control everything in your house with your iPhone. There's no question. There's already apps right now, applications for an iPhone to control your thermostats, your pool pump, whatever you may want to control in your house. Applications are already available. You can already do that. In addition, you're going to be able to control your appliances, or your appliances are going to control you. And ultimately, these appliances are going to be able to work in ways that will help the grid, help you, still allow you to keep your beer cold